How did engineering innovation allow a bridge to span this vast valley and become the tallest in the world?
Defying gravity, defying nature.
How did engineers rip up the rulebook to build this hotel upside down in an abandoned quarry?
When a building is flipped like this, then things that you would normally take for granted need to be completely reconsidered.
And what happens when you attempt a world first to build a forest in the sky in the middle of a city?
That is a huge amount of extra weight that the building needs to absorb.
This is the age of the extraordinary.
Where else can you swim from one skyscraper to the other 300 feet in the air?
Where ingenious engineers have unleashed unchecked creativity.
Everything in this building pushes at the boundaries of what's possible.
Building structures so outrageous, they defy logic.
The forces on this thing look like it should be torn apart.
Now, their secrets revealed. Discovering the incredible stories of their construction.
These are extraordinary feats of engineering.
To try and understand, how did they build that? What happens when a road that carries up to 50,000 cars a day needs to cross a river?
Crossing over a road, river, or valley? That's easy. Build a bridge.
But what if that river is in a valley that's 300 meters deep, 2.5 kilometers wide, and happens to be in one of France's most beautifully unspoilt regions? The answer is to hire one of the world's most visionary architects and assemble a team of brilliant engineers to construct the most advanced bridge possible.
You know something is at the cutting edge of engineering if you have to design a brand new system to deal with it.
The Milan Viaduct is the tallest structure in France and the tallest bridge in the world.
Nothing has been done exactly like this. Each big bridge is a new bridge.
It cost 300 million euros and took 15 years to create a bridge so special that people traveled from around the world to see it. So, how did they build it? It's quiet now, but in the late 1990s, the sleepy town of Milan in the south of France was a snarled-up bottleneck on the old tourist road from Paris to the Mediterranean coast.
Imagine peak holiday, the route from Paris to the Mediterranean, and the traffic just slows down. You've got 20-mile nose-to-tail pollution.
Relief, though, was on its way in the shape of a new auto route to the Med that 240 kilometers south of Paris would finally bypass long-suffering Milan. But there was no way around the massive Tarn Valley where the town lies. The valley is a vast, steep-sided 2.5-kilometer wide split in the massive Central Plateau. Deciding exactly how to cross it wasn't easy. Michel Villager was on the project right from the first planning stages in the late 1980s.
The first idea was to go slightly down in the valley and to come up. And finally, somebody, a road engineer, said us, but why do you go down in the valley? We could not answer. And so we said immediately, we look at it.
So architects were asked to design a bridge to span the whole valley. And in 1996, the plan from Foster & Partners won approval.
Our interpretation as a team was to march across the valley from plateau to plateau with the most efficient, the lightest impact on the landscape, and create a series of spans. And along the way, you would bridge over the Tarn.
Building such an extraordinary bridge would turn the project into a laboratory of engineering innovation on a massive scale. The whole bridge weighs 290,000 tons and is made up of 3 major components. 7 giant concrete piers rise up from the valley floor, on which rests a 2,460-metre-long road deck. To top it off, 7 huge pylons tower above the piers, with tensioned cables supporting the road below. Because these cables send the load directly back to the pylons, which are balanced by an equal load from the opposite side, the cable-stayed bridge design is very efficient. To realize the slimline, elegant design would take innovation at every stage of construction.
That demands a feat of engineering on a completely different level, something extraordinary.
At the start of construction in 2001, the first things to be built were the 7 huge load-bearing towers, or piers. Building a road deck at this height had never been attempted before. They were so tall that the engineers had to turn to skyscraper technology. The builders used a technique known as climbing formwork. Each pier had its own platform and mold, which would create a 4-metre section at a time. Once the concrete had been poured and set, hydraulic jacks pushed the mold up so that the next level could be poured. But as the piers grew, getting the concrete up to the top to pour became more and more difficult.
That's where cranes come in. But the piers were so high that the cranes had to be tied to them for stability.
With robot-like efficiency, all 7 piers grew 4 meters every 3 days. They took 21 months to reach road level, by which point each contained 16,000 tons of steel and 85,000 cubic meters of concrete. Next came the road. 8 steel sections were assembled on site at the valley's edge, but lifting them into position with the crane at this height would be too dangerous. Incredibly, despite weighing 36,000 tons, these sections would be slid out across the top of the piers. But this posed a serious problem.
If you use a classical technique, you will have to push the piers, and in addition, you have friction. And the piers would not have resisted these forces because they are very tall.
The friction caused by sliding the sections of road over the piers could cause them to fall over. But the team came up with an ingenious solution.
So the idea was to develop a launching system which do not introduce any horizontal force on the piers.
What they used to lay the bridge deck of the Milan viaduct was a complete one-off.
The team constructed 7 temporary metal piers. On top of all of the piers, computer-controlled hydraulic platforms would lift and move each road deck along very slowly out towards the center, with the middle road decks already rigged with 2 pylons. Launched from both sides, the road decks moved just 600 millimeters every 4 minutes, 5 times slower than a snail, until they met in the middle.
Each piece would move forward inches at a time. It took days to get the whole thing into place.
With each deck taking up to 3 days to reach its final position, this process was very vulnerable to one of the region's most unpredictable threats. Winds in the Tarn Valley have been recorded at 200 kilometers per hour, but even much lighter winds would cause problems during the critical deck launches.
Every morning, the site receives the weather prediction, and we decide not to launch if we have not 5 days in front of us with less than these 37 kilometers per hour.
Can you imagine what would happen if a giant piece of this road deck got caught up by the wind? And it would cause really bad damage.
Working around the clock for 2 days, the central sections, complete with the 2 middle pylons, were finally within touching distance. Global positioning systems had been used to plot their path. Despite starting at different heights and with a gentle curve throughout the 2.5 kilometers, when the roads met, they were within the 1 centimetre tolerance. The final component was not entirely crucial to the engineering, but was a fitting way to celebrate an incredible piece of innovation.
It was inventing how you would make the bridge, and that magic moment when, you know, from 1¼ kilometers coming together, that 2½ kilometer, and they magically touch.
The road was complete, but it wasn't designed to solely rest on the 7 piers. It needed to be supported at much more regular intervals to be strong and rigid enough to take the loads of the bridge deck and 5 million vehicles a year traveling across it. This would be done by massive cables.
The Milan viaduct is what we call a cable-stayed bridge. It makes use of thick steel cables to support the weight of the bridge and lock the structure together at the same time.
The cables would be hung from 87-metre-tall pylons, each on top of a concrete pier. The prefabricated steel pylons weighing 700 tons had to be installed in one piece. Loaded onto massive transporters which crawled across the bridge, the pylons were then inserted into a frame and pivoted into position. The 7 pylons would share the job of supporting their own 5,000-ton section of road, each from just 22 tensioned steel cables. Expected to have a lifespan of at least 120 years, the bridge needed to be easily maintained. So a secret tunnel was built in, running under the road. Camille Baudel is a tour guide.
We are inside the deck of the Milan viaduct, and we are just underneath the roadway joint. That's why we can hear the noise of the vehicles passing on it. And the joints are here to absorb the movements of the deck, because when it's very hot, the deck expands, and when it's cold, it's retracted like this. So the joints are here to open and close all the time.
Being a road bridge, accidents have to be considered, especially a crash that causes a sudden weight imbalance, which could be catastrophic.
So these balls are here because if there is an accident on the traffic and a lot of liquid pours into the deck, these balls will float, so the liquid can go down and there is no more weight inside the deck.
Finally, in December 2004, 1 month ahead of schedule, the first cars rolled across this stunning strip of tarmac. Now 5 million vehicles pass over it a year, and people even take detours just to experience its magic.
Initially, you couldn't cross because everybody was stopping their cars and photographing, because a lot of people make the journey just to see the bridge, as well as to enjoy the speed of the crossing.
The Milan viaduct pioneered new ways of building and did it in record time. A remarkable achievement for a proud team.
A 3-year adventure for 500 people. Everybody coming from different disciplines, different backgrounds, and wanting to achieve something that was truly outstanding, something that had not been done before, and something that would turn making a car journey, a truck journey across this 2.5 kilometers in the sky, kind of ethereal experience.
Each bridge is a prototype. You use ideas which generally already exist. An engineer must know what was done before and must be able to reuse the good ideas which exist. A colleague said, engineers are climbing on each of our shoulders.
Most buildings in Shanghai try to reach for the skies. But just a few kilometers west, designers and engineers have flipped this habit on its head. Here, they have gone down, down, down. Nestled into a 90-meter-deep quarry is an incredible new building that offers a true escape from reality.
This place is part Thunderbirds, part Bond villain lair. It's even got a shark pool.
But this is no film set. It's the world's first underground hotel. Creating this 49,000 square meter upside-down hotel with underwater floors meant turning engineering on its head.
When your building's flipped like this, everything that you take for granted is just thrown into the air.
It took 12 years and $300 million to engineer a way around earthquakes, floods, and crumbling rock. But the result is a world first. The 336-room subterranean Wonderland Hotel. So how did they build it? Back in 2005, before the project started, this disused quarry, a 30-minute drive from Shanghai, was earmarked to become the exact opposite of a tourist destination.
The government planned to make this place as a treatment place for the garbage.
But a developer had a vision to create a hotel with a feature so unique that people would travel from around the world to experience it. Tasked with turning this site from garbage can to gold mine was architect Martin Jochman.
When I first the quarry, actually it was completely overgrown and the water level was quite high. It was more like a lake, which was surrounded by old industrial buildings and overgrown vegetation.
Martin used the location's natural assets as a starting point for his design.
The inspiration for the design came from the quarry and from the greenery, from the rocks, from the waterfalls. And it needed to span between the ground level and the bottom of the quarry itself. This was what would make it really outstanding and spectacular.
Martin was keen to create a building that fitted naturally and seamlessly into the environment. What appears to be just a 2-story grass-covered complex at ground level is only the tip of the structural iceberg. Hidden below is the main 16-story hotel room section of the building. The design embracing shapes from within the quarry. One half curves out, the other curves in. Between them is a waterfall-like glass atrium, which houses the elevator shafts and services. But it's at water level where things are most unusual. Here, huge 5-meter-deep aquariums hold over 300 tons of water, meaning the lowest 2 floors of restaurants and guest suites have huge windows onto an extraordinary underwater world.
What I tried to do is to create a building mass that joined with the quarry and became part of it. It became part of the overall character of the quarry itself.
In 2011, as the 5,000-strong construction team began work, this challenging site threw up its own unique set of problems. Before the engineers could start building the hotel, they had to prepare the quarry itself, which had been abandoned for years.
Before we start building construction, we have to make sure the condition is okay for building works. And as you see, the cliff here is not very stable, so we have to solve this problem.
So how do you prepare a giant hole filled with water for an underground hotel? First, the team drained the quarry of 10 meters of water before turning to the rock faces, which would need to fit the hotel structure.
The quarry had to follow the shape of the building itself. But also, because of the safety requirements, we needed to do some stabilization of the rock faces themselves. Some of the rock faces had to be blasted, but not too many.
The quarry is comprised of andesite, a type of rock formed during a volcanic eruption. It's solid in places, but can be crumbly and unstable, creating dangerous conditions for anyone below.
It is pretty amazing to see behind this building, because it looks from the outside as if it's all fixed to the wall. But actually there's a huge cavernous space behind it, and it's really only fixed at the top and at the bottom.
The team came up with a solution. 15-meter steel bolts were driven deep into the rock at 2-meter intervals, creating a huge grid. The compressive force of these 6,000 bolts knit together the loose rock. For added security, a metal mesh was anchored across the bolts and sprayed with a thin layer of concrete. All this is still visible from the inner atrium.
It is pretty amazing to me how well the concrete has weathered to colour match the original walls over time.
Only once this was all done could they begin work on the massive foundations. They would require 60,000 cubic meters of concrete into which steel trusses would be embedded. But pumping all that concrete from ground level down 90 meters wasn't as easy as you might imagine.
Until it sets, concrete is a delicate mix of materials of different sizes and weights, and it has to be continually mixed.
Getting the concrete down was probably the most important and most difficult to solve. We all know how to pump concrete high to build skyscrapers, but pumping it down 90 meters is a different story altogether, because gravity can separate the parts of the concrete and can weaken the concrete.
On the journey down the chute, the size and weight of the different components that made up the concrete fell at different speeds, separating out by the time it reached the bottom of the quarry. So the team came up with a simple but incredibly effective solution to ensure that the concrete stayed mixed.
The builder had to create remixing stations on the way down the quarry, where the mix of the concrete would be collected, remixed, and sent down again, so that when the mix got to the bottom where it needed to get to, it was the right consistency.
This innovation was just one of the ideas pioneered as engineers tried to overcome the site's unique challenges.
This method was patented, so it's one of the, I think, 38 or so patents that the builder had to create to realize this building.
By 2015, the foundations and substructure were completed, and work had begun on the next levels. But the build faced another challenge. 7 years prior, the devastating Sichuan earthquake that left 87,000 dead and 5 million homeless prompted the Chinese government to enforce strict seismic building codes across the country.
But when you have an earthquake, then what's happening is that the ground is shaking violently from side to side, and it's that sideways force that has to be carried down into the foundations. So if a structure is in an earthquake zone, then it has to have a way to resist that sideways motion, or it will fall down.
To prevent a catastrophic collapse, buildings in earthquake zones are often set apart from the ground using isolator pads.
Base isolators are essentially like suspension, but for a whole building. This means that when the earth moves because of the earthquake, the base isolators absorb that movement, leaving the rest of the building completely undisturbed.
The Wonderland Hotel, though, couldn't use this technique in the traditional way, as it had a fundamental difference.
Normal buildings have one point of contact with the earth, at the bottom. Here you need to connect the top, where people enter, with the bottom, where the weight of the structure is. The problem is that during an earthquake, these might move in the opposite direction. And when that happens, well, you have a hotel falling in a hole.
To prevent the top of the building tearing away from the bottom during an earthquake, both ends of the structure needed to move independently of each other. So a radical solution was needed. First, a series of inverted L-shaped steel trusses were embedded in the concrete base that is rooted to the quarry floor. This creates a rigid joint at the bottom of the building that reduces the lateral movement of it during a quake. It was in fact at the top of the building where traditional isolator pads would be used.
The worst case scenario, if it was fully rigid, would be that the whole building collapses and it's a major disaster. The way it's been designed was a rigid connection at the base, and then at the top had to sit quite loosely on the edge of the quarry so that it would enable any movement in case of earthquake.
So the engineers turned seismic isolation technology upside down.
They've used a form of seismic isolation, which means they've taken that top section, they've sat it on a series of separation joints, steel plates, which means that the sections can move independently.
16 floors up at the top, the building isn't fixed onto the rock. Instead, the upside-down L-shaped trusses of the structure rest on the concrete lip that runs around the quarry wall. A set of steel isolators sit between the trusses and the lip, allowing the building to slide back and forth in the event of an earthquake.
This is to allow for minimal damage to the building rather than the whole building collapsing.
Water was key to the design of this complex. And in 2018, one of the last phases of construction was refilling the quarry with over 200 million litres of water. It would take 6 months, but would also pose one of the biggest threats to the hotel and its guests: flooding.
You've got twice the annual rainfall of London coming down into a waterproof rock hole. Plus, there's a waterfall pouring water in, and a river, and a canal, all within overflowing distance.
Prone to typhoons and monsoons, this coastal region is one of the world's most vulnerable to flooding. So the team came up with a solution that could instantly address the smallest increase in water.
In order to maintain this water level, we have a very powerful emergency pump, and this will come into operation if there's too much water coming into the quarry. It could be through exceptional rainfall, or if there's some breakage into the quarry from the canal. So this can then deal with that situation.
Fully automated and computer controlled, the emergency water pumping system is programmed to keep the water level within a 500 millimeter tolerance. 6 pumps are at the ready to evacuate 800 cubic meters per hour into the surrounding canals. The next challenge was to create a suitable ecosystem for exotic fish like these. The 2 underwater floors needed to have spectacular views to warrant the $3,000 a night price tag for these exclusive suites. But the quarry lake was too dark and vast to guarantee guests a glimpse of Jaws' little brothers.
The client envisaged that part of the building would be underwater, but no real instructions as to how to deal with it. So I suggested that we put aquariums below the water level to face the guest rooms or the restaurants. So the client really agreed that we should put themed tropical aquaria with some sharks in it as well.
Separate from the main body of water in the quarry, these self-contained aquariums would be huge. 5 meters long and over 5 meters deep, containing 40 tons of water. The engineers needed a material that would be strong enough to withstand the pressure of the water and clear enough for the guests to see the display. Normal glass wasn't up to the job.
Glass is perfect for small aquariums, but when you're trying to hold back many tons of water like you are here, then it's just too brittle, meaning that a small crack could be catastrophic.
Upping the depth of the glass was pointless. The thicker the glass, the more opaque it becomes. The solution was to use acrylic.
Acrylic can be as thick as 200 millimeters, 300 millimeters, and you can still see clearly through it.
The largest of the acrylic aquarium windows the engineers installed weighed over 4 tons, but revealed the underwater idyll in all its glory. In 2018, the Intercontinental Wonderland Hotel finally opened its doors to the public. It had taken 12 years of hard graft and amazing engineering to overcome an array of complex problems. But against the odds, Martin and his team created this extraordinary building, the world's first underground luxury hotel, an outstanding achievement for a site once earmarked for the rubbish heap.
This project is an example of taking a scarred piece of land and turning it into something beautiful, luxurious, and even natural. But above all, it's an amazing piece of engineering.
Cities are growing more crowded by the day. Greenery is being pushed back to make room for concrete. But what if it didn't have to be that way? In Italy, radical designers and engineers are pioneering a new approach to both urban expansion and environmental regeneration.
This idea was a bit crazy, like having trees on a building.
These trailblazers have rethought how city life could be, lifting a forest into the sky, creating a stunning, life-giving sculpture.
It feels like this futuristic version of what buildings should be.
What many of our cities and urban areas are crying out for is more green space. This could be the solution.
Engineers had to create a structure strong enough to hold a hectare of forest and tough enough to withstand high winds, all while battling vibrations from subway trains. So how did they build it? Milan is a city of 70 square miles. Almost all of it, dense urban sprawl. But packing people in has meant sacrificing something important.
Green spaces are an essential part of the city's ecosystem. Not only do they do the obvious thing of absorbing carbon dioxide and emitting oxygen, but they give us humidity, they collect dust, and create an ecosystem for insects and animal life. All of these things together make the city a more hospitable and pleasurable place.
Starved of the space to create a traditional garden, a developer decided to think outside the box.
Developers love challenges, so the big theme was how can we reintegrate the neighborhood into the city and having the opportunity to do it through the nature. There was a strong commitment by all of us in making a sustainable project.
The answer was to create a building that could hold all the plants of a park on the ground within a vertical structure. This would be Bosco Verticale, or the vertical forest. Structural engineer Luca Buzzoni was brought in to make it possible.
As a structural engineer, I must admit I was skeptical about it. You typically don't put big trees on tall buildings because of additional weight, because of wind forces, and those sort of things.
Luca's doubts were well-founded. No building like this had ever been attempted. On these structures, plants came first, and they would impact the way the buildings were constructed, so an unusual collaborator was needed. Laura Gatti is an agronomist, or in layman's terms, a plant whisperer.
This building has been designed for trees. We make calculation on what the trees is needing to survive, thinking to be a tree and thinking like a tree. This is not a building in which the greening is put just for decoration.
Normally, the landscaping is the last part of the project, but here the plants are actually built into the fabric of the structure, and the design of the structure is led by the needs of the plants. That's pretty standard for a greenhouse or an arboretum, but it's not that usual for an inner city block of flats.
This unusual brief for up to 27-story apartments that were half giant plant pots would result in a unique and complex plan. The ambitious design called for 2 residential towers that would rise 110 meters and 76 meters from the ground. Cantilevered terraces would extend 3.5 meters from the structures. These would have to be strong enough to hold 900 trees and allow them to grow up to 6 meters in height. In addition, 16,000 other plants would act as cladding for the building. Construction began in 2009, with 6,000 workers on site. Their first challenge came from Milan's public transport system.
The buildings on this project have been built either on top or very close to existing metro tunnels. So it was quite a challenge to build big buildings on top of those tunnels.
27-story buildings like these would normally need concrete piles drilled deep down into bedrock for stability. But with the subway carrying 1.4 million commuters every day right underneath, the engineers had to find a way to give their buildings a strong base without touching the tunnels. And they inadvertently struck gold.
It was possible to design shallow foundations even if the buildings are pretty tall and pretty big, because the soil in this part of the town is very good. It's made of sand and gravel, so the capacity of the ground is pretty high.
Although the ceilings of the subway tunnels were as little as 3.5 meters below ground level, the engineers could cautiously build on top of them. During construction, a 24-hour monitoring station was set up to keep an eye on any stresses exerted on the tunnels below. So now the foundations wouldn't interfere with the subway, but the vibrations from the trains could still ruin the living conditions for the building's occupants. So the engineers turned to a solution often used to protect buildings in earthquake zones.
So basically what this system makes is very similar to what you have in a normal car with a shock absorber. So in the same way, shock absorbers take vibrations from the irregularities in the roads and damp them down.
The vast buildings were floated on a bed of base isolators made up of steel springs. The springs act as dampers for the vibrations from the trains, so the earth is free to move below the building, while the structure remains insulated from the subway line underneath. With the building and trains effectively isolated from each other, the engineers could tackle the most unique challenge of this project. They had to design a structure to cope with the hundreds of plants and trees and the soil they live in, whose weight and size constantly change. To complicate things, many of these plants would live around the edges of huge cantilevered balconies. Cantilevers are a trick of engineering. These reinforced concrete slabs look like they're suspended in space, when they are in fact internally fixed to support columns within the main structure. But they are usually designed to bear a limited weight.
So when I think about these balconies, I think about the fact that they're essentially experiencing cantilever action. So not only is it carrying the weight of the plants in the soil, but any moisture that's in the air that gets trapped into the soil is just adding to the load and therefore increasing the amount of reaction that the attachment has to resist on the exterior of the building. And so the fluctuations of the loads or the weight on these balconies really does change as the seasons and the humidity changes.
The engineers came up with a way to make the balconies incredibly strong to counter the weight of the trees and plants.
We have post-tension slabs, and what that means is that in concrete slabs we normally only have steel rebars. In this case, we also have steel cables, and those steel cables are pre-stressed so that the presence of the cables in the slabs provide additional resistance and additional stiffness.
So, as well as predictable, stable steel and concrete, these towers would also be shape-shifting organic structures with dynamic loads that needed to be understood and controlled as much as possible.
This is a live building. It changes season after season, and it grows year after year. So it's not something normal on a project. So what we did, first of all, we tried to understand how to cope with the changing life of the buildings.
It was crucial the experts identified plants that gave the engineers a chance to design a building that could cope.
We select trees that are not allergenic or not messy tree, and we understand which are the position on the building in which the wind is higher than other parts, and we select the trees to thrive this condition.
That wind was the biggest concern. A large tree in a strong wind could put serious strain on the building, and the wrong trees could badly damage the structure. The team needed to know as much detail as possible before choosing these potentially destructive elements. A selection of trees were tested in a wind tunnel to assess if they were suitable for high-rise living.
First of all, we had a set of tests in the wind tunnel here in Milan to understand the behavior of the trees together with the behavior of the building, to see if the presence of the trees was introducing additional forces on the building, and to understand the magnitude of the additional forces on the building. And then we had a second set of tests in Florida.
At Florida International University, they have built the Wall of Wind. Here, they can build whole buildings and blast them with hurricane-force wind to see how they stand up.
The tests helped to determine which trees were the perfect weight and shape for the building. But there was another, more basic worry that had to be addressed. If a small tree on the ground is knocked over by the wind, it can be a small problem. If a tree falls from a large building, then you've got a very big problem.
If a tree falls from the 27th floor, everyone is going to know about it.
With 2-meter trees planted 27 stories high, no one wanted to take any chances.
For most of the trees and all the medium and tall trees, we have cables that basically provide an additional anchor for the trees in case they break, so that they cannot fall over during windstorms, for instance. And then for all the big trees, and especially for all the positions that we identified as possibly critical because of high wind velocity during windstorms, we provided an additional anchoring system that basically connecting the root ball of the trees to the concrete structure so that they cannot fall over.
It took 3 years to create this tower block oasis, which was officially opened in 2014. These 2 buildings are proof that people can have it all. Enjoy life in the metropolis and a taste of nature right outside their high-rise window.
I think it's also great that a person can look out their window and see what looks like a forest growing on their balcony when in fact they're in the middle of an urban area.
The engineers who built Bosco Verticale overcame new challenges and achieved the best of both worlds, pushing sustainable green spaces skyward, offering a glimpse of the future for city dwellers.
It's a brave example that shows that something different is possible, that healthier cities are possible for us.
The strong commitment and passion by all of us made a project that at the end has become today a symbol, an icon for sure.